For every billion particles of antimatter born in the first second of the universe, there were 1,000,000,001 particles of matter, just one extra. The rest, billion against billion, annihilated each other. What remained from that annihilation was light, filling space in every direction, and from that one extra particle in every billion, everything else. Every galaxy, every star, every hydrogen atom in Earth's oceans. This is a story about antimatter, about what it is, where it came from, where it went, and why the lopsided answer to a physics equation turned out to be the most important fact in the history of the cosmos. Let's start in 1928. A young British physicist named Paul Dirac is trying to do something that sounds straightforward. Write down the equation of motion for an electron, the simplest charged particle there is, in a way that obeys both quantum mechanics and Einstein's special relativity at the same time. Not an easy task. Quantum mechanics and relativity had been developed independently and didn't naturally fit together. Dirac managed it. The equation he produced is now carved into the floor of Westminster Abbey, where he is commemorated, and it is genuinely beautiful. 4 coupled differential equations compressed into a single compact expression using matrix algebra. It predicted the electron's behavior with precision that no previous equation had approached. But the equation had a problem, or rather it had 2 solutions. One solution describes an electron with positive energy. That's fine. That's your normal electron, the one orbiting the nucleus of every atom in the periodic table. But the second solution describes something with negative energy. In classical physics, you might say, ignore it, it's unphysical. But quantum mechanics doesn't let you do that. If the mathematics admits a state, nature can access it. The second solution had to mean something. Dirac's response was to build a picture. Imagine all of space, every point in the vacuum, completely filled, packed, absolutely solid, with electrons occupying every possible negative energy state. An invisible ocean of electrons everywhere at all times, already there before any experiment begins. He called it the Dirac Sea. Now imagine punching a hole in that sea. Remove one electron from the negative energy ocean. That absence, that hole, would behave like a particle in its own right. It would have the same mass as an electron, because it represents a missing electron. But it would behave as though it had positive electric charge, because where there was a negative charge, now there is nothing. The hole is positively charged. It moves through space like a particle. It scatters off other particles like a particle. To every detector you point at it, it looks exactly like a particle. Dirac's picture was strange, and he knew it. For a brief time, he wondered if this whole particle might already be known, if it might be the proton. The proton is positive and much heavier, but perhaps the interactions with the C electrons could account for the mass difference. It couldn't. The math didn't work. The hole had to have the same mass as the electron, whatever this thing was. It wasn't in the existing catalog of particles. In 1932, Carl Anderson was studying cosmic rays, high-energy particles that constantly rain down on Earth from space, using a cloud chamber, a device that makes particle tracks visible as trails of tiny droplets. Anderson placed his cloud chamber in a magnetic field. Charged particles curve in magnetic fields. Positive one way, negative the other, and the tighter the curve, the lower the momentum. He was seeing electrons all the time. He knew what an electron track looked like. Then he saw something odd. A track with the curvature of an electron, same mass, same momentum, but curving in the wrong direction. Positive charge. He checked everything. He changed the orientation of the chamber, varied the field, repeated the measurements. The result was consistent and reproducible. There existed a particle with the mass of an electron and a positive charge. He called it the positron. Dirac's hole had been found in nature, and antimatter had been discovered. Today, we don't need Dirac's sea as a mental picture. It was always more intuition than rigorous theory. The modern interpretation is cleaner. That second solution to the equation isn't about negative energy, it describes a new kind of object entirely. An antiparticle. A particle with the same mass as its twin, but with every quantum number flipped. Charge reversed. Color charge reversed. Is isospin reversed. Every label that physics attaches to a particle, reversed. The antiparticle is a mirror image not in space but in the abstract space of quantum numbers. And it turns out this isn't a quirk of electrons. Every particle in nature has an antiparticle. Quarks have antiquarks. Muons have antimuons. The neutrino has the antineutrino. The equations that govern all matter, every variety of quark, lepton, and boson, every single one has two solutions. The universe, at its most fundamental level, is written in pairs. Some particles are their own antiparticle. The photon, the quantum of light, has no electric charge, no other distinguishing quantum numbers, and flipping them all changes nothing. The photon is its own mirror image. Similarly, the neutral pion is its own antiparticle, but these are special cases. Most particles have a distinct antipartner, different from themselves, waiting on the other side of the charge ledger, which raises an obvious question. If nature produces particles and antiparticles in equal numbers, why are you made of matter and not half matter, half antimatter? Where is all the antimatter? Part of the answer, it isn't hiding. Some of it is right here and has been all along. The nucleus of every atom is held together by nuclear forces. Those forces are carried by particles called pions, pi mesons. A pion is made of a quark and an antiquark, bound together. There's your antimatter sitting at the heart of every nucleus in your body. The nuclear binding energy that holds oxygen nuclei together and prevents them from flying apart. That energy is mediated by particles that are half matter, half antimatter. When cosmic rays slam into the upper atmosphere, they produce cascades of pions, millions of them, constantly. When physicists smash particles together in accelerators, pions pour out in torrents. Antimatter is ordinary, commonplace. The strange question isn't whether antimatter exists. It does, abundantly. The strange question is why the large-scale universe is so dramatically, overwhelmingly lopsided toward matter. Before we get to that, we need to understand the deepest symmetry principle in physics, because it's what makes antimatter more than just an algebraic curiosity. Modern physics is built on symmetry. Not symmetry in the artistic sense, symmetry as a precise mathematical claim that certain transformations leave the laws of nature unchanged. Three specific symmetries matter here. The first is parity, the symmetry of spatial reflection. If you built a mirror universe where left and right are swapped throughout, where every spatial coordinate is negated, would that universe obey the same laws as ours? For most forces, yes. But the weak nuclear force, the force responsible for radioactive decay, breaks this symmetry. The universe distinguishes left from right at the level of fundamental interactions. This was established experimentally in 1957 by Xian-Xiong Wu in an elegant experiment involving the decay of cobalt nuclei in a magnetic field. The discovery shocked the physics community. Until then, parity symmetry had been considered almost self-evidently true. The second symmetry is charge conjugation, the symmetry of swapping particles for antiparticles everywhere simultaneously. If you replaced every electron with a positron, every quark with an antiquark, every particle with its antiversion, would the laws stay the same? Again, mostly yes, but the weak force breaks this too. The third is time reversal, running every interaction backward. Play the film of a particle collision in reverse and ask whether the reversed film is also a valid physical process. For electromagnetism and the strong nuclear force, yes. For the weak force, not quite. Each of these symmetries alone is broken. But here is the profound fact: multiply all three together. Do all three transformations simultaneously. swap particles and antiparticles, and also flip space, and also reverse time, and the combined symmetry is exact. This is CPT symmetry from charge parity time. It is a theorem, not just an observation. It follows from the most basic axioms of relativistic quantum field theory. If CPT is violated, the entire mathematical framework of modern physics collapses. No experiment has ever found a CPT violation. CPT symmetry has a direct consequence that you can test in the laboratory. The mass of any particle and the mass of its antiparticle must be exactly equal. Not approximately exactly to every decimal place. This sounds abstract, but it connects to something very concrete. Gravity pulls on mass. If the electron and the positron have identical mass, gravity treats them identically. There is no anti-gravity. Antimatter does not fall upward. A trapped collection of anti-hydrogen atoms released in a vacuum would fall toward the floor just as hydrogen does. This was actually tested directly. The alpha experiment at CERN managed to create anti-hydrogen atoms, one antiproton orbited by one positron, trap them in a magnetic bottle, and then release them and watch where they went. The result, announced in 2023, anti-hydrogen falls downward at the same rate as hydrogen to the precision of the measurement. Gravity is blind to the matter-antimatter distinction. There is no anti-gravity drive waiting to be discovered. The masses of particles and antiparticles have also been compared to extraordinary precision through other methods. The ratio of the proton mass to the antiproton mass has been measured to better than 1 part in 10 billion. They are equal within measurement uncertainty. CPT holds. Now back to the central mystery. If matter and antimatter are so symmetrically defined, so equally real, so identically treated by gravity, why is the universe made of matter? The answer lies in the first moments after the Big Bang, when the universe was so hot and dense that particles and antiparticles were being created and destroyed constantly from pure thermal energy. Matter, antimatter, matter, antimatter, a continuous churning torrent in local equilibrium. As the universe expanded and cooled, that equilibrium couldn't be maintained. Particle-antiparticle creation requires enormous energy. Once the temperature dropped below a threshold, new pairs could no longer be produced. What remained was what was already there. And what happened next was annihilation on a cosmic scale. Annihilation is the process that makes antimatter famous, and it deserves a precise explanation. When a particle meets its antiparticle, they don't just collide and bounce. They cease to exist as matter. Their entire mass, every bit of it, converts into energy, into photons, into pure light. Take an electron and a positron. Bring them together. They vanish. In their place, gamma rays. The energy of those gamma rays is exactly what Einstein's equation predicts. E equals mc squared applied to both particles. One electron mass plus one positron mass, converted without remainder, without loss, without leftover debris, into radiation. The conversion efficiency is 100%. Nothing in chemistry, nothing in nuclear physics, nothing else in nature comes close. A nuclear fission bomb converts less than 1% of its fuel mass into energy. Annihilation converts all of it. The simplest version, called single-photon annihilation, produces one gamma ray. Two-photon annihilation is actually more common, by roughly a factor of 100, and produces two gamma rays flying off in opposite directions, each carrying half the total energy. The exact energy depends on how fast the particles were moving before they met. If they were nearly at rest, each photon carries energy equivalent to one electron mass, about 511,000 electron volts, a precise and characteristic number. Gamma ray detectors looking for that specific energy, that specific signature, can identify electron-positron annihilation happening in real time. You may have encountered this in a medical context. PET scanning, positron emission tomography, works exactly this way. A radioactive tracer is introduced into the body. The tracer emits positrons as it decays. Those positrons almost immediately annihilate with electrons in nearby tissue. Two 511 keV gamma rays fly out in opposite directions. Detectors surrounding the patient catch both photons simultaneously, and because the photons travel in exactly opposite directions, you can triangulate where the annihilation happened. Build up enough events, and you have a three-dimensional image of where the tracer concentrated, which reveals metabolic activity, tumors, areas of abnormal tissue. Every PET scan is a map of annihilation events. Antimatter, in routine clinical use, saving lives. Back to the early universe. In those first fractions of a second, matter and antimatter were annihilating at a ferocious rate, and in a perfectly symmetric universe, they would have annihilated each other completely. Every particle would have found a partner. Every antiparticle would have found a partner. And when the music stopped, all that would remain would be photons. No matter, no atoms, no stars. A universe of pure light expanding and cooling into darkness. That didn't happen. Instead, something tilted the scales. There was a tiny asymmetry, a slight excess of matter over antimatter, something like one extra particle for every billion pairs. When the great annihilation swept through, the matching was nearly perfect. A billion particles met a billion antiparticles and vanished. But that last extra particle in each billion, 1 in a billion and 1, had no partner. It survived. The photons produced in that annihilation didn't disappear either. They're still here, stretched by the expansion of the universe from high-energy gamma rays into low-energy microwaves, now detectable as the cosmic microwave background, a faint and perfectly uniform glow that fills all of space at a temperature of about 2.7 degrees above absolute zero. Every direction you point a radio telescope, you see this glow. It is the afterglow of antimatter's destruction. A universe-spanning memorial to the annihilation that almost erased everything. And that 1 in a billion survivor fraction, that's everything else. Every proton, in every nucleus of every atom, in every star, in every galaxy in the observable universe, all of it is the leftover residue of that asymmetry. We are the wreckage that wasn't annihilated. This asymmetry, the imbalance between matter and antimatter, is called baryonic asymmetry. It is one of the deepest unsolved problems in physics. We know the asymmetry existed because we're here. We don't know why. In 1967, the Soviet physicist Andrei Sakharov, better known to the world as a nuclear weapons designer turned dissident, outlined 3 conditions that a physical theory must satisfy to generate such an asymmetry. First, there must be processes that can create more baryons, protons, neutrons than antibaryons, rather than always creating them in equal pairs. Second, the symmetries between matter and antimatter must be violated specifically. CPT is not enough. You need individual violations of C symmetry and CP symmetry. Third, there must be a period when the universe is out of thermal equilibrium so that these asymmetric processes can produce a net result rather than being washed out by the reverse processes. All 3 conditions are satisfied, at least in principle, within our current understanding of particle physics. The weak nuclear force does violate CP symmetry. There are processes in the Standard Model that can in principle favor matter over antimatter. The early universe was certainly out of equilibrium during the phase transitions of its first moments. The problem is magnitude. The amount of CP violation we actually measure in the decay of K mesons and B mesons, where it has been observed clearly in laboratory experiments, is far too small to explain a 1 in a billion asymmetry. The numbers don't add up by many orders of magnitude. Either there are additional sources of CP violation that we haven't found yet, or there are processes operating at energy scales our current accelerators can't reach, or both. This is one of the main reasons physicists want to build the next generation of particle colliders, not just to discover new particles, but to find the mechanism that tipped the cosmic scales. Meanwhile, annihilation continues in controlled conditions, in laboratories, deliberately engineered. The collider that occupied the tunnel now used by the Large Hadron Collider was, for much of the 1990s, an electron-positron collider called LEP, the Large Electron Positron Collider. Its primary process was annihilation. Electrons were accelerated in one direction, positrons in the other, brought to collision at 4 intersection points around a ring 27 kilometers in circumference. They annihilated. At low energies, the annihilation produced photons. But at higher energies, at specifically tuned energies, the annihilation could produce the Z boson, one of the carriers of the weak nuclear force, a short-lived particle with a mass about 91 times that of the proton. By setting the beam energy precisely to the Z boson mass, physicists could manufacture Z bosons by the tens of millions and study their properties with exquisite precision. By counting how many different ways the Z boson decays, physicists were able to determine how many types of light neutrinos exist in nature. The answer, exactly 3, not 4, not 2, 3. This was not obvious. The Standard Model contains 3 generations of matter, each with its own neutrino, but there was no theoretical reason there couldn't be a 4th generation with a very light neutrino we hadn't yet detected. The LEAP measurements ruled it out. 3 generations and no more. That constraint came directly from annihilation experiments. The quarks now listed in textbooks were also discovered through annihilation. The charm quark, the bottom quark, both discovered when electron-positron colliders were tuned to energies that produced new particles in the annihilation products. You take known matter, destroy it completely, and from the energy of that destruction, new matter crystallizes according to quantum field theory. The process is the cleanest way to explore what nature allows at a given energy scale, because you start from something you understand completely, a particle and its antiparticle, and see everything that emerges. The Large Hadron Collider today collides protons with protons, not electrons with positrons. Proton-proton collisions are messier. A proton is a composite object made of quarks and gluons, and the collision involves all of them interacting simultaneously. But even inside proton-proton collisions, annihilation happens. A quark from one proton meets an antiquark, produced momentarily from the quantum vacuum, and they annihilate, producing a Z boson or a photon. The Higgs boson was discovered through processes like this. Annihilation is embedded in the most fundamental measurements of modern physics. At CERN, a dedicated facility called ELENA, the extra-low-energy antiproton ring, produces and slows antiprotons to speeds where they can be captured and used to make antihydrogen. The alpha experiment has now trapped thousands of antihydrogen atoms, held them in magnetic bottles for minutes at a time, and studied their properties. The energy levels of antihydrogen, the frequencies of light it absorbs and emits, match those of hydrogen to the precision of the measurement. CPT confirmed once more, this time in the simplest atom that antimatter can form. If those frequencies were different, the whole framework of quantum electrodynamics would need revision. So here's what we know. Every particle has a partner with identical mass and opposite charges. The two together can vanish into light, completely efficiently, without remainder. The early universe was full of both, destroyed nearly all of both, and left a tiny residue of matter that became everything we see. That residue amounts to about 1 surviving particle per 10 billion annihilations, a number we cannot yet explain from first principles. Physicists know what asymmetry is required, know what physical conditions could in principle produce it, and cannot yet account for why the numbers come out the way they do. The same annihilation that almost erased the universe is now a tool in hospitals used every day to image tumors. The same process that built the cosmic microwave background is used to discover new particles. The same mathematics that predicted antimatter's existence tells us that gravity treats it identically to matter. The universe almost didn't happen. It happened anyway, by a margin of 1 part in 10 billion, and we are still trying to understand why. The coin is biased. We don't know why it's biased, but the bias is the reason we can ask the question.